Buenas tardes, querido público. Estamos hoy en la última charla del ciclo preparado por el IUCA sobre diferentes temas medioambientales. Hoy cerramos con una interesante charla. A mí me parece que es una charla curiosa con un título por lo menos atractivo. Lo voy a decir en castellano, que por aquí lo tengo apuntado: cuentos con moraleja para tiempos emocionantes, sobre el papel de la causalidad y la incertidumbre en la integración de la arqueología y la paleociencia. La verdad que es un poco largo, pero llama la atención, me ha llamado muchísimo la atención. Yo lo primero agradecer al doctor Marc Vander que esté con nosotros dando esta charla. El esfuerzo de dar una charla siempre es importante. Hoy será en inglés. Para los que nos vean en el vídeo no habrá subtítulos, o sea que tendrían que ponerse el Google Translator si alguno no lo entiende, pero seguro que con las imágenes fácilmente va a seguirla. Me acompaña Alfonso Abecia, compañero del IUCA, subdirector del IUCA, y que será un poco el encargado de terminar este ciclo y presentar al ponente y al otro acompañante de la mesa, que se llama Aitor. Bueno, no me enrollo más, todo tuyo, Alfonso.
No, muy breve también, gracias, Iñaki. Bueno, lo primero, estoy representando al instituto y sobre todo a la directora, a la profesora Martínez, María, que no puede venir, pide disculpas, y bueno, estoy aquí en representación. Y lo primero, dar gracias al museo por la colaboración, por la organización tan buena de este ciclo del instituto, de charlas, de conferencias que preparamos todos los años, que yo creo que cada vez está siendo más exitoso, ¿no? Y que se están tocando temas muy interesantes dentro del ámbito de las ciencias ambientales, ¿no? Y bueno, pues hoy se termina, como decía Iñaki, y eso queríamos daros gracias por habernos acogido y haber ayudado en la organización, o haber organizado estos actos, ¿no? Hoy al ponente prefiero que lo presente nuestro compañero de instituto, el doctor Aitor Ruiz, que es investigador Juan de la Cierva, creo que por poco tiempo ya, si todo va bien, ¿no? Del Departamento de Ciencias de la Antigüedad, ¿no? De la Universidad de Zaragoza, y que es la persona que ha traído por su trabajo, por su colaboración con el ponente, y yo creo que Aitor nos puede presentar a la persona que nos va a hablar esta tarde. Muchas gracias.
Muchas gracias. If you don't mind, I'm going to introduce you in Spanish. It's all right. Gracias primero por acogerlo, por hacerlo posible, además en este entorno del Paraninfo, que a mí personalmente me encanta, y creo que a todo el mundo que venga a hablar aquí da otra sensación que cualquier otro aula. No creo que no hay ningún otro sitio en la Universidad de Zaragoza como este. Gracias al IUCA por organizarlo y por acoger al colega que tengo sentado a mi izquierda, el doctor Marc Vander Linden. Voy a dar un par de pinceladas acerca de su trayectoria para el que esté en casa y lo conozca, porque él evidentemente ha venido a hablar de otras cosas y no de su vida, pero yo me lo puedo permitir. Es actualmente Senior Lecturer in Archaeological Modeling, algo así como profesor titular en modelización en arqueología. Por lo tanto, hace una investigación que es bastante multidisciplinar. Voy a intentar pasar rápido, aunque veáis que me remonto un poco en el tiempo. Obtuvo su doctorado en el año 2002 en la Universidad Libre de Bruselas, con un título de tesis que me he tenido que apuntar, que es El fenómeno campaniforme, ensayo de síntesis histórica. Como veis ahí, la vertiente todavía es más arqueológica, pura arqueología clásica, que la interdisciplinaridad que ha caracterizado luego el resto de su carrera, y por la que yo pensé que podía ser un buen ponente para el IUCA, debido a la interdisciplinaridad del propio instituto. Cuando termina su tesis en 2002 hasta 2005, obtiene un puesto en la Universidad Libre de Bruselas como estudiante de postdoctorado. En 2005 emprende marcha a Cambridge, donde todavía vive, en el que trabaja hasta 2008, durante 3 años, en el que comienza un puesto como lecturer también en la Universidad de Leicester, también en Inglaterra. Ahí se establece hasta 2012, en el que aquí sí que surge un pequeño cambio, puesto que tiene la oportunidad de volver a cambiar de sitio y es a otro de estos grandes nombres dentro de las universidades europeas. Se traslada en 2012 al University College de Londres, donde permanece hasta 2017 y desarrolla un proyecto ERC sobre el neolítico en los Balcanes, sobre la transmisión de innovaciones y del neolítico en Europa, sobre todo a través del estudio de los Balcanes. ERC, 5 años, hasta el 2017. De 2017 a 2020 obtiene un puesto de nuevo para ser lecturer, ya menos tiempo para investigar, otra vez hay que volver un poco a la docencia, en la Universidad de Cambridge, a la que ya perteneció una década antes. En 2020 se abre el instituto, el IMSET, el Instituto para la Modelización de Transmisiones Socio-Medioambientales, la traducción en castellano que acabo de hacer sobre la marcha, en la Universidad de Bournemouth, y debido a la orientación pluridisciplinar que coincide con el trabajo que él realiza, pues decide dejar la Universidad de Cambridge que estaba en ese momento, y desde 2020 se convierte en uno de los miembros fundadores de este instituto para el estudio de las relaciones ser humano y medio ambiente, que es su especialidad, sobre todo centrado en la Europa holocena, aunque en los últimos tiempos le hemos convencido para trabajar un poco en el Pleistoceno, un poquito. Y digamos que por lo que es más conocido, tiene cientos de publicaciones, bastantes de ellas de renombre, en revistas que todos conocemos, como Nature o otro tipo de medios de difusión que son bastante conocidos en nuestro ámbito. Varios libros, proyectos, bueno, incontables, aparte del IRC, lo menciono porque es el de más larga duración, pero ha tenido de British Academy, etcétera. Y bueno, sé que no le gustará que me enrolle mucho con el currículum, porque esa parte me la he tenido que buscar, no quería facilitármela, todo ese tipo de publicaciones y proyectos. Y la mayor parte del trabajo que desarrolla se basa mucho en la modelización estadística aplicada a datos arqueológicos. Entonces, al combinar esas interacciones humano-medio ambiente a través de una aplicación de matemática avanzada, pues resulta en modelos que son la base de su trabajo. Y como, bueno, I think I finished with this, and I will give the word to the Dr. Marc Vander Linden. I think you can stand up.
First and foremost, thank you very much, all of you, for coming, and thank you very much for all the people who've made this happen at every single level. All apologies, I will speak in English. I have virtually no Spanish. It may change, because my kids are learning Spanish, and at one point I will have to help them, but I'm so sorry, it will have to be in English tonight. This being said, I think I did understand a little bit of what Aito was telling about me, partly because we discussed about it. And just to give a sort of quick background of that slightly too long, far too long title, The Cautionary Tales for Exciting Times. I'm an archaeologist by training, but my trajectory has led me to work increasingly with people from other disciplines, which I think is one of the most exciting things possible in terms of all the challenges this raises. And clearly this is something that a lot of us are experiencing. But I think that also brings an awful lot of questions, and these are the cautionary tales. And I will really try to initiate the dialogue here about what I think are a couple of things that people should consider a little bit more, which are causality and also uncertainty. We tend to sometimes, far too often, take at face value all results, and especially the results coming from other disciplines. So these are a series of quotes taken from a series of the important papers that try to sum up the state of affairs in various disciplines. And if we start with, hey, as I said, I'm an archaeologist, those grand challenges in archaeology, there is this big question, which is pretty much defining a lot of what my institute is about and therefore my work, which is how have human activities shaped Earth's biological and physical system, and when did humans become dominant drivers of these systems? This is clearly an essential question, especially when you are in a world where climate change is extremely important. It's such a big question, it's obvious it is not an answer for archaeologists. It requires to reach out to other disciplines. The question is, how do we do that? And obviously also the realization that other disciplines actually are asking exactly the same question. So I've selected these two other reviews, and first I would like to highlight this question, the last question of the fundamental ecological question, which is how can the feedbacks between human behavior and ecological dynamics be accounted for in ecological models? And the reason I've highlighted this particular question is because of that word, feedback. Because instantly, we are not simply about matching data, but if we think in terms of feedback, how different sphere of activities, human activities and elements of the environment are linked together, we need to think in terms of the causality, the potential feedbacks. So already it's a little bit more complicated than that. And then there is this other one, which is about paleoecology, and question 46, how best can paleoecologists create an accessible, consistent, usable, and future-proof record of historical and archaeological sources integrated with contemporary ecological observations? The reason I've highlighted that one is because of the word sources. It's all very good to reach out, but how are we going to do that? What are the data? There is so much data around. And I'm just an archaeologist. I kind of know a little bit of my discipline. But when I start to speak with people doing climate modeling, paleoecology, with all the brands that it involves, by definition, I have my own limits. So it's all about identifying together what are the right data for the right questions, and how do we make all of this work together. And one of the things that I do quite a lot is the modeling. So I'm not going to really show a lot of computational modeling, but I'm so sorry, there's going to be a little bit of stats. So if we go for the first thing, which is the classic question, it's correlation is not causation. I mean, it's the absolute basic. We all know that. And yet, so few of us, and I speak as an archaeologist here, do that. And this is not a statement coming from me being a little bit cynical about my discipline. There was a recent review of the most quoted paper in environmental archaeology. And this is one of the conclusions of this review, which is the paucity of explicit work on causality is a problem because identifying and understanding causal relationships requires that we know what we are looking for and how to find it. And the review basically says, of all of those most quoted papers in that field, I think only 5 or 6 tackle head-on the question of causality and are being explicit about the causal processes that they are trying to look for. And as the sentence says, it's not simply about being explicit about the mechanism, but it's also being explicit about it so that you can start to track the data. You can try to interrogate the records accordingly. It's very obvious, but as I will show you, quite a lot of the work done by my discipline generally remains at the level of the correlation. We think that this should be kind of influenced by that. Let's take 2 curves and see if they just wiggle the same way. And if so, we've sorted out. I'm afraid it's a little bit more complex. Especially so if we go for the second part of this quote, which is the paucity of mentions of non-linearity and lack of concrete evidence for it suggests that either that archaeologists think human-environment relationship in prehistory were usually linear, or that we have yet to recognize that the non-linearity inherent in those relationships. We strongly suspect that the latter is the case, which is basically a very damning sentence for my own discipline. It's not simply about recognizing the fact that causality is fundamental, it's also recognizing that causality is not one way. It's not because one thing will change that the response will be simple and predictable. That's where feedback mechanism comes in. And that makes it a total dream mess. I'm actually not really going to go into the nonlinearity because that is just... But keeping that in mind should be at the forefront of any single multidisciplinary enterprise. And I think that, unfortunately, at least in my world, it is not the case. This is a horrible figure, I'm afraid, taken from a paper that we recently published in a special issue of Sustainability, where we tried to highlight the vast potential for interaction between socio-environmental sciences, so archaeology, climate modelers, and so on. And what this is all the potential processes, factors, things that one could study if you're interested in the long-term process of socio-environmental systems. And it's organized, oops, whoa, don't do that. Sorry, no, I'm going too far. It's organized, that's the right button, with recognition that some of these processes will work at different temporal scale and geographical scale. And what this figure is here for is just to say, because there are so many potential things that one could study, you really have to start thinking about what are the causal mechanisms that you want. Because otherwise, you will never get into this sort of data because it's just impossible. So I'm going to highlight two things that I have worked quite a lot on, but which are generally widely acknowledged to be fundamental in this process of how much humans have shaped the planet and have shaped the environment. One will be demographic transitions. It's a question of population. The more people there are, the more we put pressure on the environment, which is the general underlying idea. And also, I'm taking a very liberal approach here to the word farming system. So the moment people start to farm, agriculture, animals, we start not simply to manipulate animals and plants, and we change their genomes, but we also have an increasing impact, or the assumption is that we start to have an increasing impact upon the local environment, opening of fields, clearing forests, and so on and so on. And these are really the two entry points I'm going to use into these questions. This is taken from a series of papers published respectively in PNAS and in Science under the umbrella of the ArchaeoGlobe project. So the ArchaeoGlobe dataset is an initiative led by Earl Ellis from the University of Pennsylvania, when they try to aggregate as much archaeological data as possible to try to identify at what point in time and at what scale we have the building of what he calls anthropes, so landscapes which are heavily humanly modified. And whoops, once more, sorry, same mistake. Fundamentally, you have these different anthropes. The red line is the population, which goes to the maximum today. And the idea is that the more we go through time, the more you have importance of these environments where humans have built upon. And it can then be broken down in regionals. ArchaeoGlobe has been extremely powerful, and it's extremely quoted. But I think it has two problems. First, it actually does not have that much data. The way the data is organized is a problem, and I will go back to that point later. The other thing is that quite a lot of the engine that should lead to the transformation is actually not data at all. That beautiful red line here, that is not a population in the sense of past census. It's actually the output of a simulation, which is taken from the height model created by Kees Klein-Goldwaite. Don't get me wrong, height is a beautiful simulation. It's a super complex model of population and land use through the past. But it's a model. it is to some extent informed by data point. And for instance, this chart here shows, and over here, shows all of those points are population estimates taken from the literature. But that's for the period between 0 and the 17th century. And then you have more for the historical period. For prehistory, which is the period I work on, there is 1 point here. And all of that trajectory is fundamentally a set of very clever rules, but they're just rules. They do come with a measure of uncertainty, i.e. you have this envelope, and you can see that that's the minimal scenario, where there's basically nobody. There's a big scenario, and then it's somewhere in the middle, there is the average. And that is what is actually fed into our GeoGlobe. So the figure I was showing you is the regional evolution. If you dig deep into the supplementary information, there's actually another version, which is this one, which is based on the 2 different population scenarios. So that is when you have not many people, that is when you have a lot of people. I'm not going to go through it at length, but basically, for Europe, it changes a little bit the signature here compared to that, which is just the last millennium, and everything else is pretty much the same, because they don't have the data. But these data are really, really, really hard, and I'll try to get to that. There are other ways of doing that, and that's a collaborative paper where I was involved, pretty much kind of kickstarted an awful lot of what I'm doing now, where it was the outcome of a dialogue with climate modelers, vegetation modelers, archaeologists. And the question was, well, what are the key parameters that we would like to see in a series of simulations, and how can we actually shoehorn data into that? And what I was involved in are those 2 elements where we really want to try to see population empirically as much as possible, and also because we have this assumption that farming is going to be a very disruptive or very transformative event, at least try to map the earliest occurrence of farming across various parts of the globe. And I will go back to these elements again and again and again, because they are really driving quite a lot of my research. And I now need to move into really the proxy. So there are so many data, and there are so many processes, and it's sometimes very difficult to actually identify which one maps onto what. What I would like to have is a population census. I would like to know how many people there were in the past. Bad luck, this data is not available. So how do we do it? And most importantly, it's not simply a question of understanding how we do it or how we think we can do it, but also knowing that it's a proxy. It's shaky, it's not good, it has limits, it has uncertainty, and being totally explicit about that. So how do we do that? One way, debatable, I'm happy to debate, is to do this. That's what happens when you are an archaeologist. So in the past, people have cows, okay? Cows become bones, which are then dug by an archaeologist. And then hopefully, because we do not necessarily know the date, we get a C14 date with a measure of the probability of where the date is lying in the past. So far, so good. We've been doing that since Libby in 1950s. The assumption, and it's an assumption, is that when you don't have many people, they don't leave many bones, which are not necessarily very often dated, and you don't have a small line. And when you have a lot of cows and a lot of people, they leave a lot of bones, which are not dated a lot, and you have a lot of C14 dates, and then you sum all those probability, and you get those beautiful wiggly lines. It's a technique I use all the time, and it's massively faulty, because it rests on a series of assumptions. It rests on the assumption that everything survives equally. It rests on the assumption that every single archaeologist date. Okay, I know about that, and we're going to try to find ways to tackle that. Another problem, and that is potentially more fundamental, is that there is a y-axis here. That is just the sum of the probability. It is not a census. It doesn't say that there are 10 people here and then you multiply by 2 and that you have 20 people here. It just says it goes up and down. It's unitless. So it's not a census per se. It's just a fluctuation. And when you put all of these together, you can see that it's really not a good proxy. But hey, it's the only one we have so far. And I'll show you, I hope, maybe I will even convince you that actually there's quite a lot that we can do with that. Before I go into the entire population, I would really spend a little bit of time on the earliest date of farming. And that's where I need to show you, for instance, why I'm not entirely happy with the way ArchaeoGlobe, which is extremely used, is, in my opinion, a little bit faulty. So there is actually no data in ArchaeoGlobe. What they've done is to divide their research. It's the globe, and I've just taken a segment. You'll understand the shape in a second. And you have a series of polygons. And then each of those polygons have been divided in a time series with a step of 2,000 years, then become 1,000 years, then becoming 500 years as you get closer to the present. And then they've asked people to go and say, oh, I think that the beginning of agriculture falls in that bracket, but it's at the level of the polygon. So there is no variation within that polygon. It's the entire area is just colored in one go. And it comes with these big brackets. So it's really useful, don't get me wrong. As a first sketch, it's extremely powerful. But I think that the problem is that some people, and I would be tempted to say including some of the people who are behind ArchaeoGlobe, tends to take at face value these data, which actually come with a lot of uncertainty and a problem of resolution. Another way that you can try to identify the spread of farming, or the spread of domesticates, to be more precise, is to do that kind of stuff. So what you have here is a geostatistical interpolation. Every single dot is a site where we have domesticates, or which is associated with the period where we have the domesticates. And obviously the record is extremely changing. There's not a lot in Eurasia. There's a big concentration in China because of the domestication of millet and rice. The interpolation does those slightly bizarre shapes. So it's not perfect, far from it. But at least it has thousands of points behind. I mean, and it's not my work only. I've been crawling with various people who know these areas to try to identify all the C14 dates. And then it's an interpolation. It's code. The code is beautiful. You know what you've put in. You've put that, you know what the algorithm does, you can assess how much, that's why you have those really, really bizarre shape. You can control that. You can assess the uncertainty. But so I think that this is more transparent and probably more reliable because this is empirical. And then when you compare the two, so what I've done here is this is the map I was just showing you, and I've just made the difference. And you have the comparison. So when ArchaeoGlobe is too old, when ArchaeoGlobe is older by only 1,000 years, when it's in agreement, and an agreement is plus minus 1,000 years, which for the Holocene is quite a big thing, and when the interpolation is older. And you can actually see that there's a lot of areas where there are discrepancies. And it's related to two things. It's related to the state of the knowledge, and also to the fact that, very simply, the spread of farming is a phenomenon that has a very profound temporal and spatial structure. We're going to look at Iberia a little bit more. It's not happening just like that. And that is totally blind to ArchaeoGlobe. To some extent, it's not too much of a problem because they try to work at the large scale. But we also know that sometimes we need to downscale. And that's where I think that this is a much more powerful approach. Partly also because I can master that uncertainty. In the second part of my talk, and there will only be two parts, I would like to explore one particular case study on which I have been involved, and I'll show the work of one of my PhD students, which is fire regimes. And once more, the assumption is very simple. the question is, okay, when we start to have farming, do people use fire at a different scale to open field, to clean forest, and so on? And when I put Sweden agriculture in Google, this is the only nice image. It's very, very depressing. Sorry. But that's the idea. And the idea is, do we actually see a change in fire regimes linked to people, and especially the shift to farming? And we're going to look at that for Iberia. Why do we look at population? When you look at modern data, so this is based on modern satellite data, the relationship between wildfire and population is actually extremely complex. It is not a linear correlation. So what you have here is a mapping of the correlation between the population density and the density of fire. And you can actually see that in a lot of areas it's negatively correlated. So the more people, the less fire. In some areas it is positively correlated, but it's not that simple. And one example is, it's nearly impossible to see, but Iberia just comes across with a good correlation. And the reason it's so complex is because it is not a linear system. It's not the more people, the more they do fire. It has also something to do with what they do, but it also has something to do with the nature of the vegetation. Some vegetation are more prone to fire. Some vegetation are less. As one British ecologist once said, I don't know if you've ever been in a British forest, but you can picture it. It's very wet, very green. Or as someone said, it takes fire the same way as a piece of damp asbestos. It just doesn't burn that well. So already thinking about the relationship between population and fire is tricky. But we have to start somewhere. And there's actually quite a lot of literature on this question. And I'm highlighted here one example, which is a quite elegant paper in many respects, done by Snitker. So he's looking at this microregion, and he has this particular site where you have coring, and this is the evolution of the microcharcoals and the evolution of the vegetation. And you can see that around 5,000 BP, you have a clear shift here in the amount of charcoal, kind of coincide, with also a shift in the vegetation. And the question is, well, is this anthropic? Is this the signature of humans? The way Snitker tried to answer that question, and that's the reason I like the paper, is using a model. I'm not going to describe the model. It's an agent-based model, which takes into parameter the population, which is inferred based upon which is based on the density of archaeological finds here. It's a very elegant, very beautiful model. And what you have here, so that's the data that we were looking at, and that's the outcome of the simulation. And without going through all of the colors, basically you see that the trajectory here is pretty much the same, and these are all the simulations where Snitker has put in his ABM humans. And it looks good. And I remember looking at it and I thought, oh yeah, that's good. But then there's a trick. And it took me quite a while to find the trick. You have to keep going in the paper. There's this figure. So that's the number of fires. That's the fire, the mean fire size. We forget about that. And that is the reconstruction of the burned area. And you can see that you have an awful lot more fires here, especially as this episode. Every single fire is getting big. And yet, in that period, that's the reconstructed burnt area as a proportion of the landscape. So what actually the model does, and it took me a while to get, that's the distribution of the burn fire according to the model in the late Pleistocene, early Holocene. And you can see that actually it's a low intensity, but all over the landscape. And then it becomes much more intensive but in a very, very, very small localized area, which is actually entirely predetermined in the model by the distribution of the sites. So actually, I am tempted to say that he is right, but what he's looking at is one record, and he's only recording a very, very small chunk of landscape, which is very interesting. But what I'm interested in is not simply can we identify those individual case studies. What I would like also to know is, we're speaking of regimes, we're speaking of scale. Can we generalize that based on one point, or can we try to find another way of doing that? And that's the work so I have to take, I'm the third author on that. This is the work by Luke Sweeney, who is a PhD student whom I have the absolute pleasure of co-supervising, and Sandy Harrison at the University of Reading, who is co-supervising. So Sandy is a geochemist. She's in climate modeling. She's the person who was the lead author on that paper where we were trying to put all the stuff. So I've been working with Sandy for a few years. Sandy and Luke do all the charcoal. I'm only in the background helping for the archaeology. That's what I know. So what Luke has done is actually first not simply take one point, but take as many charcoal records as he could find. And then we're going to go back to our old friend, which is all the C14 we have for a segment of the Holocene, and try to see if we can map that in terms of population and see if there is a match. So when for the charcoal, I'm not going to go through all the details, partly because it's more than way out of my own expertise. So what every single sequence is Z transformed in order to be normalized, and then they all sum together, and then it's bootstrap, bootstrap, bootstrap. So you have a series of wiggly lines, which are the moving average, basing upon the window that you can change. So, and obviously you have this envelope. So it's really a measure of uncertainty here. You should not simply look at the average. You should also keep in mind that it's always going to be somewhere within that window. And then for the archaeology, we're going to do two things. Really following the protocol that with Sandy we developed. We're going to look at the population growth. Can we actually see if the population growth correlates in a way or another with those changes in the fire? And also look at whether or not we actually see a shift in the system when people start to farm. Before I go into that, I must say, and I must admit, that archaeology is not the only source of information when it comes to population. There's been quite a lot of data using ancient DNA. Really series of key papers, and I'm here just quoting the most recent long-term transect across Iberia. And the reason I'm doing that is because, once more, this complex chart shows different types of ancestry, so basically different transformation of the genomic structure potentially related to migration. And what is really key is that with the onset of farming, we see the introduction of a series of new genes which are not present in the local foraging population. So there is a migration, which already suggests that there might be more people. These kind of studies there are lots of problems with them, but I'm not going to go into that. All I want to highlight is that there's more people, there's a migration. This being said, there are some ADNA papers that are doing slightly more interesting things for, I think, our purpose. So this is another paper, and what they've done here is running a method which is conditional nucleotide diversity. Never mind the specifics. Basically what it does is that it becomes a measure of the effective population size. So the effective population size is the number of people who successfully had sex and had babies, which is not directly to the overall population, but it kind of works. And what is really interesting is this one. That's the signature for Iberia in the early Neolithic. The fact that it's shifted to the left suggests that we actually have a relatively small effective population size. So there are people, but less so than in other areas. Beyond that, for the purpose that I'm interested here, ancient DNA is not that interesting. It tells you about migration, but when you want to go further into the structure of the population, I would say that they need to beef up their act. And there are some really, really interesting things now being done, but let's close the brackets. We go back to some probability distribution. So these are relatively complex graphs. So what you do, let's take a look at this one. So my black line, that is my empirical signal. This is just counting C14. And for instance, when you have several dates from one site, we just lump it together so that you don't look at sites that are oversampled as being going completely crazy. And then, because there are so much uncertainty about what is generating that signal, we put on top, it's the work developed by a group in UCL, we put a null model. So we just say, okay, so it clearly grows up. What could it be? Or it could be an exponential. It's a basic population model that you have. The population just keeps on growing. And then you fit that model, you run it several times, and then you have this gray envelope. Says, okay, if it's a population that behaves exponentially, it should look like that. And then you can measure when the signal is above or below the expectation of the model. And you can use an exponential model, which is the basics of basics in population biology. Or you can also use, for instance, a logistical model. And a logistical model will imply, or at some point there is a change in the demographic regime, possibly related to farming. Does the model fit better or not? And you can look at the deviation, you can look at it like that. You can also look, it's exactly the same data, but you're looking at the rates of change. So the model suggests that the rate of change will be constant. When do we see deviation? And by looking at all of these, by testing several models, you can start to get a better understanding of the nature of your data. And fundamentally, there's clearly a spike here, which corresponds, roughly speaking, with the spread of farming. And it keeps pushing, and there's another big spike here, which will correspond to the chalcolytic. The fact that it gets flat, that is a pure artifact of the method. It's the fact that we don't have enough C14 after that, because archaeologists rely upon other means. But I would be tempted to say that between this point and this point, we're good. And clearly, this is not too bad a proxy. And it shows oscillation, pretty much where we expect them. And then you can do an awful lot of other statistics to identify, okay, rather than say it goes like that, where actually does it change in terms of the regime? And you can use a statistical analysis like a change point and so on. It's not perfect, but it gives, I think, a relatively accurate representation of the population trajectory, which is low, more people, but it's not a sustained growth, kind of goes up, and then there's another growth there. So we have our two proxies. We have our charcoal, and we have our C14, potentially the people. And then, because we're good scientists, we do a correlation. So that was the fun part. We were very, very good. Well, Luke was very, very good at reporting everything. So we tried every single way of doing the correlation. Correlation across the entire line. Moving window. Correlating parts where the signal is above the average in the two areas, and so on, and so on, and so on. We've tried every single correlation possible. These are all the values. It never goes beyond 0.3, which is really bad. What is even worse is that none of it is significant. It's pointless. And the reason it's pointless is because probably it's just too simple an approach. I think that most people at that point will either stop trying or will be very happy to publish a paper that says that there is no correlation. End of business. What it does say is that if, and only if, there is a relationship between population and fire regimes, it does not happen during this period. If those systems are coupled, and there are lots of suggestions that these are coupled, the coupling happens outside of the window we have. And actually we do get a little bit of a signal here, but it's so tiny that is just eyeballing, and I will not do that. So I think that this is actually an interesting result. There is nothing, potentially because the systems are not coupled. But that is just one part of the question. which is population growth. The other question is, okay, and when they farm, does it change? Which is this one. In order to do that, went back to the C14 record, and the first thing that Luke did, I was actually a little bit more involved because the geostat is something I like. Rather than using a thin line section, in this case we used a kriging, which is a geostatistical technique. So basically you take all the C14 dates associated with the early Neolithic and you try to infer a surface. And that gives you an early spread here and a clear delay, for instance, in North Siberia. You can use different parameters. So you have here, it's one representation of the success of the kriging. And basically, this is the one that we've used, but you can see that all the other surfaces are roughly comparable. So once more, it becomes a surface of uncertainty. But we're quite happy with this one. This is the one that performs the best. And that gives us the best of image available of spatially how this spread is organized. And then Luke, I have to say that is Luke's idea, did something really, really clever. He transforms the charcoal record according to the date when farming starts. So rather than taking it from between, 8,000 to 4,000, he transforms it according to what is before farming and what is after farming. And he modifies everything and then he recompiled. And you create that. So that composite charcoal is exactly the same data as before, but recalibrated according to the start of the farming in each of the points. On the assumption that if farming starts here at 5,007 or at 5,000, it doesn't really matter. If it's a linear reaction, within 200 or 300 years, we should see something. And the answer is, we don't see anything. There is a small trend of going up through time, but actually it starts way before the arrival of farming. There is nothing. We've done other types of time series modeling on that. There is just no response. There is nothing. And I think that's really interesting, because there is clearly a response at the level of the site. We have gazillions of examples of that. But at the scale of Iberia, kind of regional, super-regional scale, it does not change the fire regimes for that window, because the systems are not coupled. Probably because there is just not enough people, or they don't have enough of an impact, either in transforming the vegetation or just being enough of them. But the reason I really like that paper, regardless of the fact that it has my name on it, is because we really tried to look at it in every single way possible by keeping uncertainty at the forefront and by being explicit in the choice of our stats to say, okay, it's this mechanism or this mechanism, and try. And there's nothing. And it contrasts quite spectacularly with another paper published by Connor and colleagues, where they have less data, and they've done something that still to the day do not understand. They've looked at, they've made the distinction between the sequence where they have the maximum in the middle Holocene, the sequence where they have the maximum in the late Holocene. So they have two lines. So there is this one here for the middle Holocene, there's this one line here for the late Holocene, which I think is a little bit dubious, because if you're looking at it by putting it together, they sort of cancel one another. But what they do suggest is that there are potentially two peaks, and it does correspond to some extent to transformation in the vegetation. Our results are not entirely incompatible with that. Our results actually suggest that, yes, that may happen for periods for which we do not have the data, but I would strongly question the validity of this part here, because that I'm fairly robust that there is nothing happening. Whether or not those systems become more coupled by the Roman period or during the medieval period, that I would be happy to buy. But I have no data. There is no C14. I could count the number of sites, which is another way of doing it, but that will imply to have extensive inventories or site gazettees, that is a huge undertaking, and I think that right now it's impossible. Where it could be interesting is that this sort of questioning, if you have the right person, the right archaeologists who are willing to listen, that is a way to say, if we want to answer this question, this is the sort of data collection we want. I don't want to see all of the archaeology, but is it possible at a not too expensive cost to assemble the data, to reinterrogate the record? And that's where I think multidisciplinary research is really exciting, is when it brings your own limit and it asks you to go back to the drawing board and ask yourself, okay, I cannot provide, as I said, census, but can I find a proxy? At what cost? What will be the uncertainty? And that is really, really, I think, very important. Another thing that one can do, and I'm not going to discuss that because this is unfortunately not published, is also look at the surface and the land use. And what I do, that's an old version published in the paper, which is just to take the C14 distribution, time slice them, and then run a kernel density on top. So just basically highlighting densities. And these become areas where there is more indication of people. This is something that I've done 3 years ago. I have totally reorganized the way it works. I now have a measure of uncertainty based upon that. I am much more precise. Still not published, because we're still tweaking, but that is potentially a way to bring the spatial scale in another way. Keeping in mind that there are also caveats because it's based only on the C14, so it can only be done for certain periods. I have never been able to test it for Iberia because I just don't know the data well enough, but the method works relatively well for various places in Europe, where some of my colleagues looked at that and say it's impossible. And I said, okay, well, you just give me your distributions, and I'm going to test your distribution against my distribution. And the method is so simple, it actually performs really well. And you can bring in the measure of uncertainty. And that's going to be one of the things that we want to develop a little bit more. So to conclude, I think that my message is profoundly not original, and therefore needs to be reinstated again and again and again and again. The first one, correlation is not causation. It's so evident that we all forget about it, and it's so simple to forget about it, but it's not that side. We really need actually to consider causality at the beginning, because if we do nothing about causality, we cannot go back to those records. And those records are just too complex to be interrogated in a simple way. Uncertainty is fundamental. We try to put it on the side. We just put it under the carpet. That's a mistake. It's a fundamental mistake, especially in multidisciplinary research, because you should not trust your own record. And if you don't have the expertise to assess someone else's record, that person should be explicit about that. And then the last thing, and I think that is the greatest challenge, these processes act at different scales. And where we are nowhere is how you shift from one scale to another. How human activity, which kind of by definition is at the point, ends up building so much that those systems shift and become much more observable across larger spatial scale. How it unfolds through time. Where are those shifts? There is a beautiful theoretical literature on complex system on that. But how we test it, we don't know. But because we don't know, that is really, really, really fun to do. Thank you very much for your attention.